Hello, everyone. So today we're going to be doing a quick little side topic into some chemical safety considerations at the industrial level. So anyone who's had my sophomore seminar may find some of these rather familiar. So again, one of the things I try and want to emphasize is that when you're ending up choosing which chemicals you're going to be working with, especially as terms of precursors or as solvents where you have a little bit more flexibility, I want you to always consider what the toxicity of the material is, because this is going to really influence a lot of the cost and safety features you're going to need to build around your plant. So again, one of the things I want you to be very aware of is when most people talk about toxicity, they're almost always focusing in on this idea of acute toxicity. And many of you are probably familiar with the idea of the LD50, or essentially the amount of substance that's required to kill 50% of a population. This is usually specifically designed about talking about rats and then scaled up on a per kilogram of body mass. So again, it's worth noting that while LD50s are useful, not all toxins are going to be immediately deadly or dangerous. In fact, most aren't. And so what we have to usually worry much more about is this idea of long-term exposure. Less what's gonna not make me drop dead right there, and more what's going to kill me 20 years down the road, or say 5 years because it turns out I don't like cancer. So in order to look at these, we need to make use of what's called threshold limit values. So this is going to be the amount of substance that a worker can be exposed to 40 hours a week, every week on an annual basis. So these are the ones that will get you in the long term. So one of the things you should be aware of is a lot of what we're talking about is going to be in the aerosolized form. So if you end up working at a chemical plant that makes use of any of these materials, try and make sure that they do annual checks on the aerosolized components, because with things like ammonia, acetone, or even things like HCl or hexane, it's actually quite easy to get uh, fairly large levels of these species into the atmosphere. And things like carbon monoxide, you might not even ever know. Now, I went ahead and pulled together a small subset of these values, but a larger subset are going to be available on Blackboard. But you can also get a full list of what OSHA considers the the TLVs on the OSHA website. And so again, one of the big things is to limit a lot of these TLVs are going to be things that can be done uh, to decrease the concentration. So increasing the amount of containment or surface area that your solvents are exposed to is going to seriously decrease the amount of evaporation, increased ventilation in the work area, uh, disposal of any open containers, and again, a lot of this is going to be based on training, but don't forget that monitoring can play a rather large role. And if you're dealing with truly toxic levels, you might need to make use of things like such as protective equipment like air masks. So this addresses a lot of what we need to watch out for on the toxicity level. But turns out we also should be very aware of flammability. And this is something that we talk a little bit less about in our traditional chemistry labs. So if I want to go ahead and look at the likelihood that any chemical I'm working with is going to catch fire, there's going to be several key features I want to be aware of. The first of which is that liquids almost never catch fire. What catches fire is the vapors above the liquid. So when we're talking about flammability, we really need to focus in on any sort of chemical vapors. This may be directly above the liquid, or it may be in the wider room. So if I'm going to be evaluating how likely something is to catch on fire, what I need to actually be looking at is um, is the concentration of that flammable gas in the atmosphere. So there's going to be a minimum concentration at which any gas will catch fire. So as you may notice, this ranges typically anywhere from about 1.4 for heavier compounds like benzene or toluene, and it may go all the way up to things like uh, 10 to 15% for things such as ammonia, which are going to be a little bit harder to catch fire. And so the major idea when we're talking about this lower limit is that um, if I have too little of the vapor um, in suspension, one molecule may end up combusting, but there's not going to be any other molecules near enough for the combustion reaction to essentially run away and to ignite its neighbor. However, conversely, you also may notice that there's an upper limit. And if I exceed a certain percentage of the atmosphere, as say hydrogen or uh, or propylene, if I'm above that certain percentage, the my fuel also won't catch fire. And this can be a little bit of a mystery because we tend to think that, oh, if a little catches fire, more will be even worse. But it's worth noting that a fire requires two parts: fuel and oxygen. And if I have too much fuel in the atmosphere, this means I don't have any oxygen and the fire will quickly smother itself out. So what you have to really watch out for is going to be cases where I have some intermediate amount of fuel present in the atmosphere. So a lot of features on trying to limit flammability are going to be making sure that uh, any fuels are in a rather small container. That way, there isn't enough headspace to allow significant concentrations of oxygen present, or to make use of good ventilation to make sure that any fuel that's evaporated into the atmosphere is quickly dispersed. However, it turns out that we often need to account for temperature as well as pressure when evaluating flammability. And so in order to do this, we make use of what's called a flash point. So this is essentially the minimum material, a minimum temperature at which a material can catch fire. So for example, acetone actually won't catch fire if we're below about 0 degrees Fahrenheit, so fairly cold. However, one of the things that I think is worth noting is also, say, the flash points of things like diesel, which it turns out there's a reason we need to go ahead and compress diesel for it to catch fire, because it turns out it won't catch fire on its own, at least at 1 atmosphere. However, similarly, this is the reason why when you get up into northern Alaska, you also need to have a warming block on even your gas engine, because it also won't catch fire at any temp below -45. So again, this can be a fairly useful feature in trying to control flammabilities, because I can go ahead and try and combine these flashpoints and flammabilities to quickly dictate at what point I can deliberately set a fire, and also what conditions I can use to prevent a fire. So if I'm working with gasoline or diesel or even benzene, and I want to prevent any sort of ignition, I can make use of a refrigerator, which is often one of the reasons why you'll find a lot of flammable organics typically stored in refrigeration units. However, one of the things that's worth noting is the only difference in between essentially a fire and an explosion is essentially how compressed the system is. And this can be a little bit non-intuitive. But if you think about something like gunpowder, it will catch fire in open atmosphere. But if I confine it into an enclosed space, this is where we end up with an explosion. However, one of the things to make note of is that in order to have an explosion, we need to still have enough of a concentration of oxygen that we still exceed the that it's possible to exceed the upper threshold value. But in general, uh, when we're trying to prevent a fire, one of the big things we're going to be trying to avoid is going to be ignition sources. So the classic example here is flames or electrical sources. But it turns out that sometimes keeping a flammable substance away from an ignition source won't be sufficient because occasionally temperature alone is enough to cause ignition. And this is the idea called autoignition. So it turns out that almost any chemical can spontaneously catch fire as long as enough oxygen is present if I exceed a certain temperature. So the idea is that once I exceed this temperature, I have enough energy inbuilt into the system that I can overcome any kinetic barrier to combustion. And so making sure that you know the autoignition temperature of any chemical compound or material you're looking at can actually be quite important. Um, so for example, diesel has a relatively low autoignition temperature, and this is more or less the idea of how a diesel engine works, is that I raise the pressure high enough so that that flash point decreases enough that I don't need a spark plug. However, when I'm dealing with something like gasoline, one of the reasons I use a spark plug is because the autoignition temperature is much higher. However, one of the things you'll note is that a lot of our organic solvents tend to have autoignition temperatures anywhere from the mid 100s up into the 400s. And again, this is one of the reasons why diethyl ether is considered quite dangerous, is that it is possible to actually reach reach the autoignition temperature above system near things like hot plates. However, it's often much harder to reach the autoignition temperature of things like paper. Uh, don't forget your good old Ray Bradbury, as well as things like leather. But it turns out that you do not actually need a fire to cause these materials to burn. But again, one of the things that you should make sure to be aware of when you're trying to design or even just working in a chemical plant is to be very aware of the autoignition temperature, because at this point, any runaway reaction can quickly turn catastrophic if it's generating enough temperature to exceed these threshold values. So these are essentially going to show you what the line in the sand that you should not cross. Again, make sure to be aware if you're working at different pressure regimes, because the autoignition temperature can change. So thank you for bearing with me as I lecture on safety. Till next time, take care.